Okay, so last time we started to discuss tensor product of vector spaces. So suppose V and W vector spaces over a field K. Then the tensor product is denoted like this, and it is the set of all elements of the form, right? So this is the set of all elements of the form. V1 tensor W1, V and tensor Wn, and is a positive integer. And Vi's are from V and Wi's are from W, right? And so it is a set of all elements of this form, subject to the conditions or axes. So this is like a product. We call it tensor product, and it obeys some rules. 3 rules. What are they? First one is this: lambda times this tensor product will be the same as this one, and will be the same as again this one. So here lambda V I have, and here I have lambda W. So lambda times this tensor product is the same as lambda V times tensor product of W, tensor product of W, and V tensor product lambda V. In other words, you may put this lambda wherever you want. Okay. Second, it distributes over addition from left and right. So this is the same as this one. And similarly, it distributes over addition from left, namely this. So this is true for all lambda in V, K, V, V1, V2 in V, and W, W1, W2 in W. Okay? And we defined addition and scalar multiplication. So this gives right, this is a vector space. Vector space. Okay. With the operations, what are the operations? Well, addition is just if you have, so elements are like this. So addition operation is this. If I have 2 such vectors, let's say V1 tensor W1 up to V n tensor Wn, I have one element, another element, let's say V1 prime W1 prime up to Vm prime Wm prime. We define the addition, just the expression is one. So we go from 1 to n, and then we add the remaining terms. So this is the addition and scalar multiplication. scalar multiplication is this. Whenever we have lambda and something like this. Then we just put lambda, for example, all the terms. And again, you will put lambda either if you want in front of D or W. Okay, both of them are the same, right? Because we have this two, so this times this can be is equal to this digit and this digit. These are our axioms. Okay, so these are the rules we accept. They are not something to prove. We define this object as a vector space. Its elements are summations like this, and we have this strange multiplication which we call tensor product, and we list the rules this tensor product should obey, and then we define our vector space operation. This is the addition. So if you have two terms like this, we just put them together. And again, last time we discussed what was the zero element. Zero element is just 0 times any vector, right? Of course, you may put this 0 either here or here. So if you put it here, 0 times is just 0, so 0 times is W, or you may put it here, and then V times W. So this is V times 0. These are all the same, and it is the 0 element of the additive group of this space. Okay, under the addition operation. Yeah.
For the next doesn't for that. Shouldn't be sure that we won't run this set for this inside of this.
Yeah, but this is the set of all such elements. So if you have two such elements, then the sum is defined this way. This is another element of the same type. Yani bu vektör üzerinin elemanları bu tipte sonlu toplamlar. İki tanesinin toplamını da şöyle tarif ediyoruz. Yani bu toplamları yan yana yazıp aralarına artı koyarak. Yine sonlu bir toplam. Tamam mı? All this may look strange, but actually you will see that this is a very natural object, and actually it is kind of an object you have seen many times so far, but we just didn't call it as a tensor product. Okay, for example, determinants are just tensor products. Okay, and linear maps can be described using tensor products. We will see that also the volume element or area element you have seen in advanced calculus, or you will see in advanced calculus, they are just some tensor products. Okay, so it's a very natural object, even though its definition seems a little bit, abstract and artificial, but it is not. Okay, it's a very geometric, natural object. Okay. All right, so this is kind of the summary of what we have done last time. Yes.
Is the V1 for W1 state and W1 has?
No. Here it is V. If I say V times W, then here the first element will be from V, the second element will be from W. So V times W and W times V are different digits, But we will see that they are isomorph. Right? There is a natural isomorphism in these two spaces, but they are not the same thing. Yes. Alıyorum. Tamam. Okay, we have seen one example last time. Okay, so an exercise. So, for example, consider this gadget. Okay, both R3 and C complex numbers are vector spaces over R over the field R. Then, of course, then like this one, I have two vector spaces V and W. They are vector spaces over the same field K. Then the tensor product is another vector space over K. These are vector spaces over R. Their tensor product, then their tensor product R3 tensor C. Sometimes we put the field over here to indicate that these are both R vector spaces, and this tensor product is a tensor product over R, meaning that my scalars are real numbers. Okay, here it might be useful to use this notation because C is also a field, right? Field of complex numbers, and one may may not distinguish scalars, I mean complex scalars and real scalars. When you write R here, it means for this vector space, my field, base field is real numbers, not complex numbers. But the thing is, so you don't have to put this because I already said that these are vector space over R, but sometimes it is good to put this notation to indicate that these are vector space. These are considered as vector spaces over R. But our claim is the following: if you take the tensor product over R, then this becomes a complex vector space. Is a complex vector space. Okay, and here, of course, you know, this R3 has no special, you know, importance. You can put any R and okay, any real vector space. So if you have any real vector space, if you tensor it with C, then it becomes a complex vector space. So that's another, you know, nice property of tensor products. It allows you to extend your base field. Yes. Evet. Şimdi detaylandıracağım.
Bir daha söyler misiniz?
Efendim?
Bir daha söyler misiniz?
Söyleyeceğim. Birden fazla da söyleyeceğim. Okay, now we know what is the vector space structure on R3, right? These are just triples. We multiply them by real numbers, we add them, and so on. We consider also C as a vector space over R. What was the operation here? Of course, C vector space over R. elements of this are just objects like this. X and Y are just real numbers. And of course, the addition operation here is just the addition operation, usual addition operation, right? So if you have Z1 and Z2, you just add them as complex numbers, right? Addition operation is this. Scalar multiplication is what? So if you choose a real number, then you multiply a complex number, complex vector, whatever, with this as how. Now this is just x plus iy. So we just write this. So multiplication by a real number, you just multiply the real and imaginary part. And with this operation, C becomes a real vector space. And what is the dimension of C as a real vector space? Dimension of C as a real vector space is 2, right? And this was the basic 1 and I. Okay, very good. Now, what I claim over there is that R3 tensor C now is a complex vector space. What I mean, I can multiply the elements of that gadget not only with real numbers, but by also complex numbers. Okay, how? Okay, so the complex vector structure on R3 tensor C. I consider both of them as real vector spaces, but now I claim that this is a complex vector space. Okay, let's say this is W. And what is the addition operation? And so I have to tell you what is the addition operation here and what is scalar multiplication. Addition operation. Addition. Well, elements of this are just tensor products, right? So V1 tensor Z1, Vn tensor Zn. This Vi's are in R3, Zi's are complex numbers. And if you have two of them, let's say U1 tensor Z1 prime or V1 prime, Vm prime, Zm prime. How do you add them up? Well, just right over there, we just write them. So V1 tensor Z1 up to Vn tensor Zn, and now V1 prime tensor Z1 prime, and Vm tensor Zm prime. So this is the addition operation. What about scalar multiplication? I have to tell you what is the scalar multiplication. So what we mean by that, whenever I have a complex number this time and an element of W, so V1 tensor Z1, Vn tensor Zn in W, I have to tell you how I multiply them. So W times this gadget, V1 tensor Z1, Vn tensor Zn. I don't know how to multiply this gadget by lambda, right? Because this is a real vector space, element of a real vector space, and this is a complex number. Okay, the product of this gadget doesn't lie inside V3, değil mi? Yani bir tane reel vektörü kompleks sayıyla çarparsanız, this is not in R3 anymore, right? We don't know what is this digit? But I can do the following. This is already a complex number, and this is a complex number, and I know how to multiply complex numbers. So this product is just defined to be this digit. V1 tensor lambda Z1. V2 tensor lambda Z2. Vn tensor lambda Z2. Okay, this is how we define. So we use the second component here to multiply these objects with complex numbers. Okay. Yani ikinci komponent zaten kompleks değil, onu lambda ile çarpmayı biliyor. Bu şekilde çarp. Yeah.
Why lambda is complex number, but we say there are
No, I claim the following. The tensor product is a complex vector space. So this is my claim. I can put a complex vector space structure here, meaning that I can multiply the elements of the tensor product with complex numbers. And this is how I do. I cannot multiply a real vector with a complex number because the product will not be real. Actually, we don't know what it is, right? I know how to multiply a real vector with a real number, but with a complex number, it is not defined. But this is a complex number, so I can multiply it with lambda. And this is how I define my scalar multiplication. Come on.
Can you give the definition of complex vector?
Well, I mean, it is just a vector space. Your base field is just C. That's it. Complex vector space means your base field is C. So it should be an abelian group, and you should know how to multiply your elements with complex numbers. Think of this, R5. Is this a complex vector space? Because we don't know how to multiply these vectors with the complex numbers, right? We don't know how to multiply. Okay?
For the scalars, for the tensor product, we could just use two numbers also, right?
Yeah, of course, this is, so you are saying that this is a real vector space. It is actually, this is how it is defined, right? You see, this is, tensor product is a real vector, I mean, it's a vector space over the same base field. Okay? This is how we define scalar multiplication. This gadget is already a vector space over R. But what we are claiming is more than that. We say that we may extend the base field to complex numbers. Okay? That's something actually very important. Yes.
You said something about like vector space in the vector space. Also, we just said this tensor product is vector space on R.
Over R.
Yeah. And but can we say that this is also a vector space over complex numbers?
Yeah. Now, this is exactly what we said. Now, so our claim is that this thing is already a real vector space, we know that, but we claim that this is also a complex vector space. In other words, I can multiply the elements of the tensor product with complex scalars. And this is how I do it. And I just said that, just consider this gadget. This is a real vector space. So it's a vector space over R, over Q also, right? I can multiply because Q is also a real number. I can just restrict my scalars to Q, but I don't know how to multiply these elements with complex numbers. Okay, this is not a complex vector space. Well, one may try to put a complex vector space structure to this gadget. You may try something. For example, for R4, I can define a complex vector space structure on this guy. But you have to be, it is not straightforward. But this tensor product is a very easy way of converting a real vector space to a complex vector space. Tamam mı? Sorusu olan. Şunu silebilir miyim? Bu ne? Bilgisayar kodu mu? Quiz var. Bize de Fortran öğretiyorlardı. Basic vardı bir de. Basic'i gerçi kendimiz öğrenebiliyorduk. Basitti. Benim zamanımda Commodore 64 diye bir bilgisayar vardı. İnternette yazarsanız almıştık ondan. Basic'te böyle bir kitapçığı vardı. Oradan öğreniyordunuz. Program falan yazabiliyorduk. Yani öğrenmiştim onu. Hard disk diye bir şey yoktu. Teyp kasetlerine kaydediliyordu programlar. Sonra burada öğrenci olunca Fortran'ı öğrenmiştik. Ama unuttum arkadaşlar. Okey. Bilgisayarcı arkadaşlarım var. Bizden mezun olan, yani benim sınıf arkadaşlarım, bilgisayar şirketleri var. Bazen böyle algoritmalarda sıkıntı yaşayınca gelip bize soruyorlar. Nasıl yaparız? Yani bilgisayar dilinden anlamasanız da matematiği biliyorsanız hala orada söyleyecek bir şeyleriniz olabiliyor. O yüzden hani matematiği iyi öğrenin. Gerisi olur. Okay. Another example. So let's take D to be Rn, W to be Rn. So these are vector spaces for R. Then D factor W. So Rn tensor Rm is again a vector space over R. And indeed, if let's say E1 up to En and F1 up to Fm are bases for D and W respectively, then this set okay, EI Fj, I from 1 up to n, j 1 up to m, is a basis for Rn tensor Rm. I will prove this, but it is not easy. Okay, it's a difficult thing, but we will prove that. But first, let me show the one page there. Okay. Okay, indeed. M and W is in M, then since E1 up to En is a basis for V, this is just E1, E1, Cn, En, and since F1 to Fm is the basis for Rm, and this is in Rm, this is just D1 times F1 and Dm and Fm. So V tensor W is just C1 E1, Cn En, tensor D1 F1, Dm Fm. And then we use the properties of tensor product, namely the property that tensor product distributes over addition from both sides, and I can just move the scalars. So I'll do the following. I have n terms here and n terms here. This will be multiplied with this one, and then this one, and then this one. So I will have n terms. And then for the second one, I will get another n terms and so on. So the result will be just the following. Summation from I and j, I from 1 to n, j from 1 to n, of Ci, Ei, tensor Dj, Fj. And then we do what? So I can write this because of the distribution laws. And then I can move this scalar over here because scalars, you can put them wherever you want. So you get summation over I and j. You just put it here, dj, ci, and I can take it also outside, and then I have ei tensor ej, fj. So we have this term ei tensor fj, and the scalar is just the j times ci. And summation is, of course, I from 1 to n, j from 1 to n. Okay? So what this means that any element of this type is written as a linear combination of these elements. Therefore, hence, this set ei tensor fj, I from 1 up to n, j from 1 up to m, spans the vector space V tensor W or Rn tensor Rn. Of course, this is true not just for Rn and Rm, it is true for any vector spaces V and W. If the basis of these are given, like this one, E1 to En, F1 to Fn. Evet. Yani buraya yaptığım şey R'la R'nin özel bir tarafı yok. Genelde iki tane vektör düzeyi verilse, birinin boyutu n, birininki m ise, bunlar da baz elemanları ise tensor product için bu bir basis olacak. Ben basis olmanın iki şartı var. Right? For this set to be a basis, we need to prove two things. Any element should be spanned by these vectors. This is what we have shown. And then this set is linearly independent. That's not easy. That's the difficult part. We will just do it in a minute. Okay. Okay, next. We will go there. If so V1 and W1, W10 are basis for vector spaces. V and W respectively over the field. Then this widget, so V I tensor Wj, I from 1 up to n, j from 1 up to n, is a linearly independent set. Linearly independent set. And thus, it forms the basis for V tensor W. In particular, if I show that this is a basis, I already showed that it's a space set. So all I need to prove that it's linearly independent. How many elements do I have here? I have n many V's and m many W's. So we have n times m elements. In particular, dimension of V tensor W will be just m times n. In other words, dimension of V times dimension of W. So when you take tensor product in two vector spaces, the tensor product will have dimension which is equal to the product of the dimensions of the vector spaces. Direct sum'dan farklı. Direct sum'da toplamdı, tensor product'ta çarpım. Tamam mı? Şimdi yapalım onu yavaş yavaş. We will prove this in a couple of steps. Okay. Okay, so here, although I did, sorry, here we showed that this thing is a space set for this special examples. It is clear from the proof we provided that it works for any vector space, right? Right here, V and W can be any vector spaces. As long as these are just bases, then these elements will be a spanning set. So it is not something that's special to this vector spaces. Okay. Now we have a lemma. This is lemma 2. So you may wonder what is lemma 1. Lemma 1 is this digit. So you may consider this thing as lambda 1. That, if I have basis of Rn and Rm, then these elements form a spanning set. So lemma 1 is just this fact that, these elements form a basis, form a spanning set. Okay, now what is lemma 2? Lemma 2 is the following. If F star is an element in the dual vector space, is a covector element of the dual vector space of V, then find a map F star from V tensor W into W by the formula. I have to tell you how this map is defined. So this is how it is defined. If I apply any element of this type, VK tensor WK, VK is an element here, WK is an element here, then the value of this is defined as follows. F is a dual element, means it eats vectors and gives us scalars, right? F star is a map from V to K. So whenever we have a vector, you just feed F star with this and you obtain a scalar. So this is what we will do. We will feed F star with this vector. We obtain a scalar. I'll just multiply that scalar with WK. And where is this element now? It's the scalar multiple of a vector in W. Therefore, this is an element in W. Yani ne yapıyorum? Bu nesne V'leri yiyordu. Ona yediriyorum. Tamam mı? Çıkan nedir? Bir skaler. O skaleri de bu vektörün önüne koyuyorum. Dolayısıyla W'nun bir katını elde ediyorum. Tamam mı? Evet.
WK şu W vektör fetişler vektör değil mi?
Evet.
F star'a götürdüğü de W'deki vektör yani.
F star V star'ın içinde. O nedir? D'den K'ya bir homomorfizm. Yani D'deki vektörleri yiyor. Ve bana sayı veriyor. Skaler veriyor. O skalerlerle de ben bu W'yu çarpıyorum. Dolayısıyla bir tensor product alıyorum. Onu bir vektöre, W'da vektöre tutuyorsun.
V tensör W'ye gidiyor. Şurada da V yılda gidiyor.
Yok, bu şeyi iyi hatırlatmak için yaptım. F star neydi diye. Dual eleman ne demek? D'den K'ya homomorfizm demek. Right? F star is a covector, means that it's a homomorphism from V to K. It eats vectors and gives us scalars. If I have a product like this, I just feed this vector to F star. I get some numbers. I just multiply my vector WK with those numbers and obtain an element in the vector space. Right? This was an element in V tensor W. Now it's an element in V. W. Tamam mı? Sure.
Will you prove that X star is linear map or?
Yeah, sure. We will prove that.
You
Yes.
said that X star is from the 1238 and
Yeah.
it means that it's linear or?
Yeah, we have to prove. No, it's not clear that it's the linear map.
But then
This one is linear. This is linear. But this one, I am not sure.
you're changing the range and
Yeah, well, I mean, this F star and this F star are completely different objects. Okay? Yeah, maybe I should erase this. Okay. Efendim? Yanlış şeymiş dediğiniz diyorsun.
Yok. Yapacağız soldaki hani en alt tarafında denklem var ya. Soldaki eksiler içleri V tensor W'den eleman.
Bu tanım. Ben bunu böyle tanımlıyorum. Diyorum ki F star buna götürüyor. Bu benim tanımım. Tanıma itiraz edemezsin. Yani edersin de niye böyle tarif ettin diye edemezsin. Şuna edebilirsin. Bu iyi bir tanım. Bir kere ben bunun lineer olduğu iddia ediyorum.
Soldaki eksilerle sağdaki eksiler aynı eksiler değil herhalde.
Şöyle bu kovektör ya. Kovektör olduğu için yani evet haklısın. Bu bir notasyon, abuse of notation. Right? There's an abuse of notation here. I'm denoting two different things with the same notation. But you know, this is typical in mathematics. You don't create a notation for everything because then you have too many notations. This is an abuse of notation. You are right. Here, this is defined on this object, but then I just use this thing. So it's a map from B to K. So, okay, yeah, you are right. So there is abuse of notation here. Tamam mı? Evet. Sorusu olan var mı?
Biz aslında veren şeyi de giden bir vektör alıyoruz. Lineer map alıyoruz.
Evet.
Sonra onu tensor product'tan V'ye giden olarak. Bu ikisi
farklı şeyler. Bu şöyle, buna tüm dedim.
ama o aldığımız şeyi tanımlıyoruz.
Efendim? Artık abuse of notation kalmadı. Tamam.
Yani aldığımız lineer map'i tanımlamıyoruz. Öyle bir lineer map varsa başka bir lineer map tanımlıyoruz.
Evet. Tamam. Başka sorusu olan var mı? İyi, ara verelim. Heyecanlı bir yerde kaldık.